Imagine a world where reality refuses to behave the way you expect. A world where a particle can exist in multiple places at once, where simply looking can change the outcome of an event, and where the very act of observation seems to shape the universe itself. At first, it sounds like science fiction or the musings of a dreamer, but this is a world of quantum physics, a domain so strange, so fundamentally counterintuitive, that it has both amazed and terrified the greatest minds in science. From the earliest experiments to the paradoxes that still puzzle physicists today, the quantum world operates by rules entirely different from the ones that govern our everyday lives. In the classical world we live in, cause and effect seem simple. If you throw a ball, it arcs through the air and lands where expected. If you turn a light on, the room brightens immediately. There is predictability, certainty, and a sense of continuity. But at the subatomic level, these rules break down. Particles such as electrons, photons, and neutrons do not follow fixed paths. Instead, they behave like clouds of probability, existing in many possible states simultaneously until a measurement or observation collapses them into one definitive outcome. This principle, known as superposition, is a cornerstone of quantum weirdness. Perhaps the most famous illustration of this principle is a thought experiment known as Schrödinger's cat. In this scenario, a cat is placed in a sealed box with a mechanism that has a 50-50 chance of releasing poison. According to quantum mechanics, until someone opens a box and observes the system, the cat is neither alive nor dead. It exists in a superposition of both states. This paradox challenges our intuitive understanding of reality. How can something be in two mutually exclusive states at once? And more importantly, what does this say about the act of observation? Does reality exist independently of our measurements, or is the universe somehow intertwined with consciousness itself? Early experiments revealed that the quantum world is stranger than even the most imaginative thought experiments. Consider the double-slit experiment, which demonstrates the dual nature of particles. When electrons or photons pass through two narrow slits, they form an interference pattern on a screen behind the slits, a pattern typical of waves, not particles. But if scientists attempt to measure which slit a particle passes through, the interference disappears, and the particle behaves as if it were a solid object all along. The act of measurement changes reality itself. The particle does not merely reveal information about the system. It fundamentally alters the outcome. This is the essence of the quantum measurement problem, a puzzle that has confounded physicists for decades. The implications of this are staggering. If the universe behaves this way at the most fundamental level, then the very nature of reality is uncertain. Quantum mechanics suggests that certainty is an illusion, that before measurement, the world is a blur of possibilities. It is as though the universe is a canvas of potential, and each observation paints a stroke of reality into existence. The deterministic laws of classical physics, once thought to govern everything from planets to people, fail to apply at the quantum scale. Instead, probability and possibility rule, and the future is not written until it is observed. Entanglement, another deeply mysterious quantum phenomenon, pushes the strangeness even further. When two particles become entangled, their properties are linked in such a way that measuring one immediately determines the state of the other, no matter how far apart they are. Particles can be separated by miles, light years even, and yet an action performed on one seems to instantaneously affect the other. Albert Einstein famously referred to this as spooky action at a distance, because it appears to violate the principle that no information can travel faster than light. Modern experiments have confirmed entanglement repeatedly, leaving physicists with the unsettling realization that reality may be far more interconnected and less local than previously imagined. Quantum mechanics does not only describe obscure particles in control labs, it underpins everything in the universe. The atoms in your body, the light that reaches your eyes, the very air you breathe, all obey these strange, probabilistic laws. Each electron in every atom exists in a cloud of potential until measured, and each photon can be in multiple states simultaneously. Entanglement ensures that particles are connected in ways that defy classical understanding. The foundation of reality itself is built upon phenomena that feel alien to the human mind. Yet despite its oddities, quantum mechanics is extraordinarily precise. The theory predicts the behavior of particles with unparalleled accuracy, and its predictions have been confirmed in countless experiments. Electrons, photons, atoms, they all obey these rules exactly, even when those rules contradict common sense. This consistency is both reassuring and unsettling. It shows that the universe truly operates according to principles that are stranger than anything we perceive in daily life. The world we experience is only an emergent reality, a shadow of the underlying quantum domain. This tension between predictive success and conceptual confusion is at the heart of the quantum enigma. Physicists can calculate outcomes, build technologies, and manipulate particles with remarkable precision, yet the fundamental question remains: what is reality when it is not being observed? Do particles possess definite properties independent of measurement, or does observation bring reality into being? Some interpretations, like the Copenhagen interpretation, suggest that measurement collapses a range of possibilities into a single outcome, implying a kind of participatory universe. Others, such as the many-worlds interpretation, propose that all possible outcomes exist simultaneously, each in a branching universe, and that observation simply reveals which branch we inhabit. Both interpretations are mind-bending. One suggests reality depends on consciousness. The other suggests that the universe splits endlessly into countless parallel worlds. Both challenge deeply held intuitions about causality, existence, and the nature of time. And yet, physicists continue to grapple with these mysteries because the experimental evidence cannot be ignored. Quantum mechanics works. It predicts outcomes with unparalleled accuracy, but it also terrifies and fascinates because it defies the framework we use to understand reality. To make sense of it, scientists have devised ingenious experiments. Delayed choice experiments, for example, show that decisions made in the present can affect the behavior of particles in the past. Entangled particles continue to demonstrate correlations that classical physics cannot explain. And every new experiment seems to deepen the mystery. Reality, at its core, is not only strange, it is profoundly non-intuitive. The universe reveals itself to be a place where certainty is provisional, where observation and existence are entwined, and where the rules we take for granted are merely emergent approximations. Even with all we have learned, the quantum world retains an aura of terror. It forces us to confront the limits of knowledge, the possibility that reality is not as objective as we believe, and that the act of observation may play a role in shaping the universe itself. These are not idle speculations. They are the natural consequences of experiments repeated over decades, confirmed with rigor and verified to astonishing precision. Quantum mechanics does not yield to our intuitions. It demands that we expand them. The first step toward understanding the strange domain is to accept the paradoxes it presents. Superposition, entanglement, measurement, and uncertainty are not bugs in the system. They are features of reality itself. The universe, at its most fundamental level, is not a predictable machine. It is a web of probabilities, a network of interconnections, a theater in which observation and existence are inseparable. And in this theater, we are both audience and participant, perceiving a stage that is constantly forming, shifting, and responding to our gaze. As we explore this enigmatic realm, one thing becomes clear. The quantum world is a mirror, reflecting the limits of human understanding and the breadth of cosmic possibility. It challenges assumptions, provokes wonder, and evokes a kind of awe that borders on fear. And yet, it is also a source of profound insight, revealing the mechanisms behind the technologies we rely on every day. Semiconductors, lasers, and magnetic resonance imaging are all applications of quantum principles. In embracing the mystery, we also harness its power, shaping reality in ways unimaginable a century ago. The story of quantum mechanics is, therefore, not just a story of atoms and photons. It is a story about the nature of reality itself, a tale in which certainty is rare, possibility is abundant, and the universe is far stranger than our senses alone can perceive. And this is only the beginning. As we move deeper into quantum world, the mysteries multiply. One of the most unsettling phenomena is entanglement, a kind of invisible thread connecting particles across space. Imagine two electrons that have interacted and become entangled. No matter how far apart they drift, meters, kilometers, or even light years, measuring the state of one instantaneously determines the state of the other. This is not a trick or illusion. It is a real effect, confirmed repeatedly in laboratory experiments. When Einstein first encountered this idea, he famously described it as spooky action at a distance, a term that captures both the wonder and the unease these phenomena provoke. Entanglement challenges the very notion of locality, the idea that objects are only influenced by their immediate surroundings. In our everyday world, signals and influences cannot travel faster than light, yet entangled particles appear to communicate instantaneously, as though the universe has a hidden network that transcends space. This does not allow for faster-than-light messaging or violation of relativity, but it does suggest that reality is more interconnected than our classical intuition allows. In some sense, the universe behaves like a single vast entity, with distant parts entwined in ways we are only beginning to comprehend. The observer effect adds another layer of intrigue. Quantum systems exist in multiple possible states until they are observed or measured. Take the classic example of the double-slit experiment. A particle, like an electron, fired through two slits creates an interference pattern, a hallmark of wave behavior. But the moment scientists attempt to detect which slit the particle goes through, the interference disappears, and the particle behaves as a single entity. Observation changes reality. The very act of measurement forces the universe to choose among its myriad possibilities. This raises profound questions. Does consciousness itself play a role in shaping reality? Are we passive witnesses to events, or active participants in the unfolding of existence? Some interpretations of quantum mechanics suggest a connection between the observer and the observed, hinting that mind and matter are intertwined in ways we do not yet understand. Others argue that observation merely triggers a natural process, a collapse of possibilities, independent of human consciousness. Regardless, the philosophical implications are staggering. Reality, it seems, may not exist as a fixed backdrop. It may be responsive, fluid, and intertwined with awareness. Entanglement and observation are not merely thought experiments. They have practical, measurable consequences. Quantum teleportation, for instance, uses entanglement to transmit the state of a particle from one location to another, instantaneously recreating it elsewhere. While this does not move matter faster than light, it demonstrates the astonishing reality of these connections. Quantum cryptography relies on entanglement to create communication channels that are provably secure, because any attempt to intercept the transmission alters the system in a detectable way. Here, the eerie rules of quantum mechanics are harnessed, turning what once terrified scientists into tools of technological revolution. The more we probe, the stranger the universe becomes. Consider quantum superposition at the macroscopic level. While electrons and photons routinely exist in multiple states simultaneously, researchers have found ways to coax larger systems, collections of thousands or millions of atoms, into superpositions at least temporarily. These experiments blur the line between the microscopic and macroscopic, revealing that the principles of quantum mechanics are not confined to the invisible world. They suggest that the strangeness we fear may be the very foundation of the reality we take for granted. Even time is affected by quantum phenomena. Certain experiments suggest that measurements made in the present can influence the outcomes of events that, classically speaking, have already occurred. While this does not allow us to rewrite history, it challenges the linearity of cause and effect as we perceive it. The quantum realm seems to operate with a more fluid notion of time, where past, present, and future are intertwined in a web of probabilities. In this strange theater, motion and state are inseparable, and the universe resists the neat categories our minds impose. Some physicists have suggested that this interplay between entanglement, superposition, and observation hints at a deeper structure of reality, one in which information is fundamental. In such a view, the universe is composed not merely of particles and forces, but of bits of information, continuously interacting, influencing, and collapsing into definite states. Spin, polarization, and position become not just physical properties, but expressions of the flow of information. And if information underlies everything, then consciousness may play a subtle role as the ultimate observer, a participant in the cosmic dialogue of cause, effect, and possibility. Despite its strangeness, quantum mechanics is extraordinarily consistent. Predictions about entanglement, interference, and measurement outcomes are accurate to many decimal places. Technologies that rely on these principles work flawlessly. Lasers, semiconductors, MRI machines, and quantum computers all function because the universe obeys these uncanny rules. This duality, Terrifying conceptual strangeness paired with precise predictability is at the heart of the quantum enigma. Reality behaves in ways we cannot intuitively grasp, yet we can manipulate it with certainty. The paradox of quantum mechanics is both humbling and inspiring. On one hand, it reminds us that the universe is far stranger than we can imagine, that even the simplest questions about reality, what is here, or what exists before we measure it, do not have simple answers. On the other hand, it shows that through careful observation, experimentation, and reasoning, we can understand, predict, and even harness these mysteries. The cosmos is not only a place of wonder, but also a laboratory, offering clues to the deepest structure of existence. This is why quantum mechanics terrifies and fascinates in equal measure. It confronts us with uncertainty, interconnectedness, and the possibility that reality is not absolute. Every entangled particle, every collapsing wave function, every superposed state is a reminder that our classical view of the world, solid, predictable, and local, is incomplete. The universe operates according to rules that challenge our intuition, yet these rules underpin everything, from the atoms in our bodies to the distant galaxies in the night sky. And yet, even in this strange and uncertain world, there is beauty. The dance of particles, the intricate patterns of interference, the invisible threads of entanglement. They form a hidden order, a delicate balance between chaos and structure. It is a world in which possibility reigns, where the universe is not fixed but fluid, where observation and existence are entwined in a perpetual dialogue. Next, we will explore the implications of these quantum mysteries for reality itself. We will examine how entanglement stretches across the cosmos, how measurement links mind and matter, and how the universe's underlying strangeness may hold the keys to understanding consciousness, information, and the nature of existence itself. As we venture further into the quantum realm, the strangeness deepens. One of the most astonishing features of this world is non-locality. The idea that particles can be linked across space in ways that defy classical understanding. Entangled particles do not merely correlate by chance. Their states are fundamentally connected, instantaneously, regardless of distance. This challenges our most basic notions of reality, suggesting that the universe may be interconnected in ways that surpass our intuitive grasp of space and time. It is as if the cosmos itself is a web, with invisible threads weaving distant parts together into a single unified whole. The implications of entanglement extend beyond physics into the realm of philosophy. If particles separated by light years remain linked, then reality is not strictly local. The universe cannot be fully understood as a collection of independent parts. Every interaction resonates elsewhere, creating an intricate network of cause and correlation. Some interpretations hint that observation plays a role in determining outcomes, implying that consciousness may not merely perceive reality, but, in some subtle way, participate in shaping it. These ideas have sparked debate and discomfort among scientists because they blur the line between observer and observed, between mind and matter. Consider again the observer effect, magnified in thought experiments like Schrodinger's cat or the delayed choice experiment. In a delayed choice scenario, decisions made after a particle has passed through an apparatus seem to retroactively influence its earlier behavior. While time travel in the classical sense remains impossible, the phenomenon challenges our linear conception of cause and effect. At the quantum level, the universe allows multiple possibilities to coexist until an observation forces a definite outcome. Measurement does not merely reveal reality. It participates in its creation. This interaction between observer and system has profound implications. It suggests that reality is not a static, pre-existing backdrop, but a dynamic interplay of potentialities. Every measurement, every interaction, every act of observation nudges the universe into one configuration or another. Even at the level of electrons and photons, the cosmos is participatory. Possibilities collapse into facts not passively, but through a process that bridges the quantum and the conscious, the abstract and the tangible. Superposition remains a cornerstone of this strange domain. In classical physics, an object exists in a specific state at all times. A car is either in the garage or on the street. An electron, however, can occupy multiple states simultaneously. Its position, momentum, and even spin can exist as a cloud of probabilities until measurement. This is not an approximation or a temporary confusion. It is the intrinsic nature of quantum systems. The paradoxical nature of superposition forces us to reconsider what it means for something to exist. Reality, it seems, is probabilistic, fluid, and only partially determined until it is observed. The consequences ripple outward. Quantum phenomena govern everything from the behavior of atoms in your body to the processes in distant stars. Electron superpositions dictate the structure of matter, the formation of chemical bonds, and the very fabric of solid objects. Photons' entanglements carry energy and information across space, facilitating the light that illuminates our world and the technology that powers our civilization. The strange, intangible rules of quantum realms shape the visible universe in ways that are both subtle and profound. Physicists have developed various interpretations to reconcile these bizarre observations with reality. The Copenhagen interpretation, one of the earliest, asserts that quantum systems do not possess definite properties until observed. Measurement collapses the wave function, forcing the system into a single outcome. In contrast, the many worlds interpretation suggests that all possible outcomes exist simultaneously, each in its own branching universe. In this view, every quantum event spawns a multitude of realities, all equally real, though we perceive only one. Both interpretations are consistent with experiments, yet each carries implications that stretch the imagination and challenge our understanding of reality. Quantum mechanics also suggests that information is fundamental. Every particle state carries information about its possibilities and constraints. When two particles interact, they exchange information instantaneously, sometimes across vast distances. Spin, polarization, position. These are not merely physical properties, but vessels of information, shaping how particles behave and interact. Entanglement, in this sense, is a flow of information that transcends space, hinting at a deeper structure underlying the cosmos. The connection between quantum mechanics and consciousness remains a subject of fascination and debate. While mainstream physics does not claim that human minds control particles, the act of observation is central to the theory. It raises questions. Could consciousness itself be a participant in the unfolding of reality? Is the mind simply reading the universe, or is it an element in its manifestation? These are questions that science struggles to answer definitively, but they underscore the profound mystery at the heart of quantum mechanics. The universe is not merely a machine. It is a participatory arena where observation and existence are intertwined. In practical terms, the quantum world is not confined to thought experiments. Technologies such as quantum computing, quantum cryptography, and MRI machines all exploit the principles of superposition, entanglement, and measurement. The very devices we use to communicate, explore, and heal rely on behaviors that defy classical logic. Engineers manipulate quantum states, entangle particles, and harness the flow of information to achieve feats that, a century ago, would have seemed like magic. In this way, the frighteningly strange laws of the microcosm become tools of extraordinary power. Even time and causality behave unusually in the quantum realm. Experiments demonstrate that quantum correlations do not always respect the classical order of events. Entangled particles react instantaneously, regardless of distance. Measurement can retroactively affect states. While these effects do not violate relativity in terms of transmitting usable information faster than light, they suggest that the underlying structure of time in quantum mechanics is far more subtle than our everyday experience implies. Past, present, and future are intertwined in a probabilistic dance where certainty is provisional. Ultimately, the quantum enigma forces a profound reconsideration of reality itself. The classical picture of an objective, predictable world is incomplete. In its place lies a cosmos of potentiality, of probabilities that solidify only through interaction and observation. Spin, superposition, entanglement, and measurement are not quirks. They're the operating system of existence, guiding every particle and every process. Reality is active, participatory, and in some sense, astonishingly alive with possibility. As we approach the final part of this journey, the question looms larger. What does this mean for the universe as a whole, and for us as conscious beings observing it? Part 4 will explore the ultimate implications, tying together the quantum mysteries with the fabric of reality, the flow of information, and the philosophical reflection that emerges when we confront a world far stranger than we ever imagined. As we arrive at the final chapter of this journey through quantum realm, the implications of what we have seen begin to take on a larger, almost philosophical dimension. The universe, when examined through the lens of quantum mechanics, is not a static, pre-written script. It is dynamic, uncertain, and astonishingly interconnected. Every particle, every interaction, every act of measurement participates in the ongoing creation of reality. What we once assumed to be fixed and absolute, the existence of objects, the flow of time, the separateness of space, is revealed to be far more fluid, more subtle, and more profound. At the heart of this mystery lies entanglement, the invisible web linking particles across space and time. Experiments have repeatedly demonstrated that entangled particles maintain correlations even across vast distances, as if they share a hidden channel of communication. This is not metaphorical. It is a mathematical and experimental reality. Entanglement implies that parts of the universe cannot be fully described independently. The whole contains more than the sum of its parts. It hints at a cosmos in which connections are fundamental and separation is only apparent. In such a universe, the idea of an isolated object loses its meaning, and interaction becomes a defining principle of existence. Observation adds another layer to this enigma. Measurement does not merely reveal a pre-existing state. It seems to play a role in determining the outcome. In the double-slit experiment, electrons behave as waves when unobserved, but as particles when detected. Schrodinger's cat remains in superposition until the box is opened. The act of observation is not passive. It is active, shaping reality as it is perceived. While consciousness itself may not create reality in a mystical sense, it undeniably participates in the collapse of possibilities into facts, highlighting a deep interplay between the observer and the observed. The universe, in other words, may be participatory rather than merely objective. Quantum superposition reveals another startling truth. Until a system is measured, multiple possibilities coexist. An electron can occupy several locations. A photon can take multiple paths, and particles can exist in many spin states simultaneously. This challenges the very notion of definitive existence. Reality, at its most fundamental, is probabilistic. What we see as a solid, definite world is a result of countless collapses of potentiality, shaped by interactions and measurements. The familiar world is an emergent phenomenon, a manifestation of deeper, underlying uncertainty. The implications of quantum mechanics ripple out from particles to the very nature of information and reality. Particles carry information about their states, interactions, and histories. Entanglement transmits correlations across space instantly, suggesting that information is a fundamental element of the cosmos. In some interpretations, the universe itself could be thought of as an information processing system, where the flow and collapse of information give rise to the structure and behavior of matter. The quantum world teaches us that reality is not merely a collection of things, but a network of relationships, probabilities, and interactions. From these principles emerge practical consequences. Quantum mechanics underlies modern technologies, from computers and lasers to MRI machines and secure communication systems. These tools exploit phenomena that, just a century ago, would have been considered impossible. The very fact that we can manipulate entanglement, control superpositions, and harness quantum properties to perform tasks demonstrates the power and consistency of these terrifyingly strange laws. What is intellectually unsettling at the conceptual level becomes astonishingly productive in practice. Yet, the deeper philosophical questions remain. If reality is participatory, probabilistic, and interconnected, what does that mean for consciousness, free will, and our understanding of the universe? Are our perceptions shaping reality in a subtle, indirect way? Does observation tie us more intimately to the cosmos than we have previously imagined? While science does not yet provide definitive answers, the quantum realm forces us to rethink our assumptions about objectivity, determinism, and the nature of existence itself. Even time and causality are challenged in this strange domain. Entangled particles react instantaneously. Delayed choice experiments suggest that future measurements can influence past states, and superpositions reveal that multiple outcomes can coexist until resolved. Time, rather than being a rigid line of cause and effect, appears flexible and probabilistic at the quantum level. Reality is not merely unfolding along a fixed trajectory. It is an emergent tapestry woven from interactions, measurements, and possibilities. The quantum universe is simultaneously alien and intimately connected to us. The principles governing subatomic particles shape the atoms in our bodies, the light reaching our eyes, and the technologies we use every day. Entanglement links us indirectly to distant events. Superposition underlies the stability of matter. Measurement, in all its forms, reflects the interplay between the observer and the observed. In short, the strange, terrifyingly counterintuitive laws of the quantum world are not abstract curiosities. They are the foundation of everything we experience. Perhaps the most profound lesson is that uncertainty is a fundamental feature of reality, not a limitation of knowledge. The universe does not present itself in a deterministic, predictable way. Instead, it offers a field of possibilities, a space where observation, interaction, and information shape the unfolding of events. This uncertainty is not a flaw. It is a source of creativity, novelty, and the richness of the cosmos. Life, evolution, and the very structure of matter rely on probabilistic behavior at the microscopic level. The strangeness of quantum mechanics is, in fact, the engine that drives the complexity and diversity of the universe. In embracing the quantum enigma, we confront the limits of human intuition, the boundaries of knowledge, and the mysterious interplay between matter and information. We see a universe in which reality is participatory, interconnected, and probabilistic. A universe in which observation matters, connections transcend space, and a familiar world emerges from a foundation of profound uncertainty. It is both humbling and exhilarating, a reminder that the cosmos is far richer, stranger, and more beautiful than we ever imagined. The quantum world does not yield easily to our understanding, and it does not conform to classical logic. Yet in its strangeness lies a deep and subtle order. Entanglement, superposition, measurement, and information are the threads that weave the fabric of existence. They show us that the universe is alive with possibility, responsive to interaction, and structured in ways that transcend ordinary experience. It is a reality that is both terrifying and magnificent, challenging our perceptions while empowering us to explore and shape the world in extraordinary ways. Finally, the quantum mystery serves as a reminder of our place in the cosmos. We are not mere spectators. We are participants. Our observations, our measurements, and our inquiries are part of the unfolding story of the universe. The strange and eerie rules of quantum mechanics are not distant curiosities. They are intimately connected to the world we inhabit, the life we live, and the consciousness that allows us to wonder. In this realization, awe replaces fear. Curiosity supplants uncertainty, and the terrifying strangeness of the quantum world becomes a gateway to understanding the profound beauty and complexity of reality itself. The universe spins, entangles, superposes, and unfolds, and we are entwined within it. This is the final truth of the quantum enigma. Reality is alive, uncertain, and infinitely mysterious, and through our observation, we are woven into its ongoing creation,